So this one is going to be property prediction, but for mixtures and related to phase equilibrium. So I just show you the plan again. So, and the references on slide 43 are different now. They are for mixture properties and phase equilibrium properties. So now let's first, even though you may be familiar with the computation of phase equilibrium, I will give you a conceptual overview of this. So let's assume that we have a two-phase closed system that could be liquid and vapor. And we have a liquid of some composition and a vapor of some composition. If the original charged molecule, charged composition, that was Z, is equal to X, then we have only liquid. If the original charged composition Z is equal to Y, then it's all vapor. If it is neither of these, then we have a mixture of liquid and vapor. And this closed system, let's assume, is controlled at temperature and pressure. So in that way, we can fix the pressure, change the temperature, and the system with the original Z composition will split into X and Y compositions, meaning liquid and vapor, which will be in equilibrium. So we need to calculate the equilibrium. So we need equilibrium model. And also we want to know what are the property values of the liquid and vapor which are in equilibrium. So what do we need to do then? The sequence of calculation, if it is the liquid phase, we need to know the mass balance. So what is the composition in the liquid phase? And if we know the composition and we are controlling the temperature and pressure, so we know the temperature, pressure, composition, through phase equilibrium, we would be able to identify the phase state. Is it bubble point because it's liquid? Is it mixture, bubble point, and some vapor in there? And also, if we have the liquid, we can also calculate for the liquid composition at the temperature and pressure, the density, volume, the enthalpy, entropy, everything. Okay, so it goes in this sequence. First, we need to know the composition, then we fix the temperature, pressure, so we can calculate the state. Once we know the state, then we can calculate all the other properties dependent on the state. What happens to the vapor? Sequence is exactly the same. The only thing is that the parameters are different and the model is different. The model for the liquid is not the same for the model for the vapor. The model for the density for the liquid is not the same for density of the vapor. Similarly, enthalpy, entropy. So we need to know the phase identity so that we can calculate the mixture properties. Okay. So now we will see also which properties and how they can be calculated. So, as I said, if we have two phases, then we have a liquid and a vapor in equilibrium. So that would be a typical diagram where on the y-axis we have temperature, on the x-axis, the red is the liquid, the blue is the vapor. At a fixed temperature of 376, if we have a composition of 25, which is the feed composition Z, it will split into a liquid and a vapor at the same temperature. And those liquid and vapor will be in equilibrium. The liquid will be at its dew point, bubble point. The vapor will be at its dew point. That's a typical vapor-liquid equilibrium. If instead we have two liquid phases instead of vapor phase and liquid phase, then you can see the blue is one side of the liquid phase diagram and the red is another side. So this is a mixture of benzene with an impurity, or let's say a product So benzene is the chemical we don't want, but a little bit of product goes with the benzene, as we can see on the red side. And the blue can be the product. So no benzene goes with the product, but some product goes with the benzene. And what we need to do then is to extract this product from the benzene. So we would need a solvent to extract it. But what we see is that at 450, at an equimolar mixture of pure compound of the product and benzene, it splits into one liquid with pure product and the other liquid with benzene with some of the product. So that's liquid-liquid, binary, but ternary, we will have to add the solvent, and we will add a solvent that can remove the product from benzene. And if we wanted to make a solid-liquid separation, then the point on the red curve, on the side of the red curve that is shown, will show that the solute, if it is at that point, it will be at the saturation point. Above the red line, it is liquid. Below the red line, it will be solid plus liquid solution. So from the saturation point, if we reduce the temperature, we will get some solid forming. And then at the bottom, you see the eutectic point. And after the eutectic point, the red curve on the left, it will be showing the saturation point for the other compound. If we are doing a rectangular diagram like this, y-axis is the temperature, x-axis is the mole fraction. So around 0.3 to 1, compound 1 will crystallize out. Between 0 and 0.3, compound 2 will crystallize out. So if we want compound 1, we need to be in a composition after 0.3. If we want compound 2 to crystallize out, we need a composition to the left of 0.3. Okay, so now you can see that thermodynamics can actually help us with the feasibility of the separation process. So here we can see again in more detail, we have two phases. Because the vapor phase and the liquid phase compositions are different, you can see it's 55% and 35% at a given temperature. And because there is a difference in composition, we can have a separation. If the vapor phase goes up and the liquid phase goes down, we have a separation, right? So this is a feasible separation. It is possible by distillation. And the bigger this difference, the better and easier the separation. Now let's look at this diagram. Now for a part, there is still separation between vapor and liquid, but we also have the azeotrope. So which means that around 40%, the driving force between vapor and liquid, that is the difference between vapor composition and liquid composition, will be 0. Because at the azeotrope, vapor and liquid have same composition. So if we want to make a separation now, and we want pure, like in here, we want pure compound 1 and pure compound 2 as the two products at top and bottom, we cannot get that here because we can get only one pure compound. The other compound will be the azeotrope. So what it clearly says is that if we wanted two pure compound in a distillation column, this would be impossible unless the azeotrope moves with pressure or unless we can break the azeotrope with a solvent. So that's again, the advice and the solve role of thermodynamics. As I said before, if we wanted to recover the product from benzene, then we would put a solvent. The solvent will be on the left, on the right-hand side. The raffinate, that is benzene, would be on the left-hand side, and the product will be the extract that will be at the top. And if we can get a two-phase region, then we can extract the product from benzene, and we can have a liquid-liquid extraction first, and then we recover the solvent and recycle the solvent. By the way, the figure, the two-phase diagram, doesn't show that this will be actually a very good liquid-liquid extraction, because the boundaries, the phase boundaries of the two-phase region, the tie lines, a better solvent would touch the two sides of the diagram. Then it would be very good. But if it is like this, then we will always lose some solvent, and some product will always come. Some benzene will always come with the solvent. We don't want that. And then, as we talked about solid-liquid equilibrium, if you want to design a crystallizer, then let's say we have a point that you see. If we evaporate the solvent or anti-solvent, that is water, could be, or some other chemical, and we move into the two-phase region, from the liquid to the two-phase region, then by definition we get some solid plus the liquid mixture. But that is called evaporation. We can also do crystal cooling from the point that you see. If we go down in temperature, this will be cooling crystallization. Either way, if we can go inside the two-phase region, we get the solid and we get the amount of liquid, which can be calculated out very simply by the inverse Lieberman rule. So phase diagrams actually help us to calculate everything that a simulator, by solving model equations, will do. So if we can provide these data to the simulator, it will converge almost immediately. Okay, so we have seen examples of phase equilibrium for the design of process separation processes: solid liquid, liquid liquid, vapor liquid. So now what properties are needed and what property models are needed for computation of phase equilibrium? So first I will give you examples, and then we will see more details. So let's first say that we know that we have a two-phase system. We have given the composition of one phase and at least two of the variable values: temperature, pressure, and phase identity. Let's say that we have given temperature, pressure, and the one phase composition. So based on the mixture, we can calculate PVT relationship, pressure, volume, temperature relationship, and phase compositions in equilibrium. Or we can just calculate the phase compositions in equilibrium. Which one we will do depends on which model we use and which chemical system we have. We will see it later, but which model we use? If you have heard of cubic equations of state will do the PVT as well as the phase equilibrium compositions. The CPA equation of state, which is not a cubic equation, will also do that. Both of them need as parameters the critical temperature, critical pressure, eccentric factor of each of the compounds in the mixture. So now you see why the pure compound properties are needed. We can also use a well-known equation of state these days called PC-SAFT. PC-SAFT does not need TC, PC, omega, but it needs some other structural parameters. M is a size parameter, sigma and epsilon, that has to do with the bonds and the energies. So knowing the structure, it is possible to calculate the three parameters. And if we know those three parameters without needing TC, PC, omega, we can do the PVT and the phase equilibrium compositions. If we use Gibbs energy-based models, molecular or group contribution, then we also don't need the TCPC or the molecular structural parameter, but we need molecular size and volume data. That can be molecular size, volume data, or group size and volume data. So depending on which type of system we have, which type of model we have, we will need different types of parameter. The GE models will not give us the pressure, volume, temperature relationships. It will just give us the phase compositions, and we will have to separately calculate the PVT relationships with another model. So now let's give some examples. I have 4 slides on this for 4 different types of examples. What I will show is the chemical system with the given information, which phase calculations to do, what type of phase equilibrium is involved, what type of conditions need to be satisfied, and what type of property models to use. So first will be examples with organic systems, and we will show the condition for equilibrium. I'm not going to derive those conditions, but I think you know those conditions very well, but I will point out how they can be obtained. So let's say the first one is benzene toluene. It's a hydrocarbon system at low pressure and 0.4 benzene. We want to calculate the bubble point and dew point of this mixture, and we want to make an entire binary PT-XY diagram. So what is involved is VLE. What is involved as condition is that at every condition, phase equilibrium condition that is defined by a mixture, defined by a pressure and a temperature, for every compound, this condition has to be satisfied. It's called the isofugacity criteria. It is a necessary condition, but not sufficient. We need to minimize the Gibbs energy, and from the Gibbs energy and the chemical potential, one can get this isofugacity criteria. So from this isofugacity criteria, we see that we need the fugacity coefficients in the liquid phase and vapor phase. These are the properties. And which models will give us those? Any cubic equations of state, non-cubic equation of state, any equations of state will give us the fugacity of the vapor and liquid for every compound. And then we have to check whether this condition is satisfied. If this condition is satisfied, then the compositions correspond to the compositions in equilibrium. This is at 1 atmosphere. What about a multi-component mixture at 20 atmosphere? And we want to calculate the bubble point. If it is multi-component, we cannot do a binary PT-XY diagram. So we will do the bubble point and dew point calculation. We need the VLE at every point. We need to satisfy the equilibrium condition. And the same model can be used. Equations of state. What about if we have methyl acetate and methanol? We want the bubble point, dew point. We want also the binary PT-XY diagram. For this mixture, equations of state, like the cubic equation of state, cannot be used because it makes an error in the liquid phase fugacity coefficient. So we can use either mixed models, combine equation of state with a GE model, or we can use GE model for the liquid phase and assume ideal vapor phase. So that is the lower equation, or we can get the vapor fugacity from an equation of state, the activity coefficient on the left-hand side from the GE model, and the PSAT is the saturation vapor pressure at a given temperature. So we need the vapor pressure model, we need the activity coefficient model, we need the fugacity coefficient model. And the fugacity saturated is a pure compound fugacity coefficient. We can set it to assume it to be negligible, then we get the lower one. So then we see that depending on the mixture we have and the calculation we want, we have to choose different model, and we also have to choose different conditions to satisfy for the equilibrium. And based on the different models to choose from. So just a quick guide for which kind of model we should use. So we have gamma phi. That means we use activity coefficient and fugacity coefficient, or we use an equation of state where we use fugacity coefficient for both phases, okay? So if we want to choose the fugacity coefficient for both phases, one option we have is cubic equation of state. High or low pressure, it doesn't matter, but the system should be ideal or slightly non-ideal, but not highly non-ideal. If we have high-low, ideal, or non-ideal, then we need to have, we will see afterwards, how we can combine an equation of state with the GE model. It is not the gamma phi, it's a combined EOS GE model. Or we can use some other more complex equation of state like PC-SAFT, SAFT, CPA kind. They will be applicable for high, low pressure, ideal, non-ideal. If we have low pressure, but non-ideal, then we use the GE model for the liquid phase, and ideal phase most of the time is, vapor phase is most of the time assumed to be ideal, or we can use an equation of state. Okay, very simply, this is some simple rules to choose your criteria for the models. So now let's look at other examples. Now we are talking about big, large molecule, which is paracetamol, which is chemical name is acetoaminophene with ethanol. And we want to know, ethanol is the solvent, at what condition paracetamol will start to crystallize out. And then the condition for equilibrium, you can see on the equation. If only paracetamol is crystallizing out, the left-hand side can be set to 1. And what we want to calculate out is X, knowing the activity coefficient, knowing the heat of fusion, knowing the melting point, and the operating temperature. Okay? But this is at 1 atmosphere. Also, you can see in this equation, there is no pressure. So pressure actually is not a variable here. If we have water, ethylene glycol, furfural, that also is a highly non-ideal mixture. So equation of state cannot be used. At low atmospheric pressure, we will have liquid-liquid equilibrium, and we use activity coefficient for both phases. So we need the activity coefficient model, not an equation of state. So for SLE also we need activity coefficient. For LLE we need activity coefficient. How about if we have water, ethanol, benzene? This is a ternary system, and it may have 3 phases, 1 vapor and 2 liquid. So this can be satisfied by adding 2 conditions, the equilibrium condition between the liquid-liquid and the vapor-liquid condition for the bottom equation. And then we need model for the liquid phase, model for the vapor phase. And we need the vapor pressure model. So what about electrolytes? We have, let's say, sodium chloride, potassium chloride, water at 1 atmosphere between 298 to 398. We want to know which salt will crystallize out at what temperature. We need SLE, and then the equations that will give us the saturation curves is the first 2 equations, and the bottom equation called solubility index gives a number. And if that number is greater than 1, then it means that the salt already has crystallized. If it is less than 1, then it has not crystallized. Note that in this case, compared to the previous ones, where we just had the equilibrium condition, now in addition to the equilibrium condition, we also have the chemical equilibrium condition. Why is that? Because the salt in the presence of water will dissociate into ions. So we have a chemical reaction going on. So K salt is the chemical equilibrium constant, and the other equation is the physical equilibrium. So we satisfy the physical equilibrium and the chemical equilibrium. So we need a model for the chemical equilibrium, which is C as a function of temperature, or we can minimize the Gibbs energy. And on the right-hand side of the top equation, we have the physical equilibrium where we need to provide the activity coefficient. If we have another mixture, is the same thing, SLE, the same kind of model. Note that here, the pressure is 1 atmosphere. What about if the pressure is bigger, higher? Then we have to use equations of state. So PC-SAFT can be used, CPA, equation of state can be used for electrolytes also. Okay, but the model is different. The parameters that will calculate the equilibrium condition will be different. So if you want pressure effect, you need an equation of state. If you ignore the pressure, then the activity coefficient models, which are very well known for electrolytes, can be used. If in addition to water, you want to have an organic solvent like ethanol, methanol, things like that, then the reference point for the equations need to be changed. Because at this moment, because of the chemical equilibrium calculations, the reference point is for water. But if there is water and solvent, the reference point needs to be changed. So the last one is polymers. If we have isoprene with methyl-ethyl ketone, we want to calculate bubble points, dew points, PTXY diagram. It is possible, but it is with a like a mixed model, equation of state for the vapor assumed to be ideal, and the liquid phase, we need the activity coefficient, and X is the saturation point concentration. It is also somewhat easier because the polymer will not vaporize, so we know that in the vapor phase will be only NK. So the right-hand side will be 1, and so it is easier to calculate the composition. If you have polystyrene with acetone or polystyrene with benzene and methanol at different temperatures, and we know that this will not be vapor liquid but liquid liquid, then we again need the liquid liquid condition and the Gibbs energy based model for both phases. If we have polyvinyl acetate with water, we can also, this will be vapor liquid because the water will vaporize out, and then we can use the fugacity criteria and we can use an equation of state. So what you see is that depending on the condition, chemicals, we can have different models that will be needed. So before I go to the next selection, next topic, which is selection of property models, I want to briefly show you the calculation steps for phase equilibria. So you have an idea, and it's a simple conceptual example. Let's say we want the bubble point temperature, VLE calculation, and the system is ideal. So in equation 2, you can see that the fugacity and activity are not used. If we want to use fugacity and activity, we just put that, and the calculation will be more difficult. Otherwise, we need just the vapor pressure. So we are given the liquid composition and we are given the pressure, and then we want to calculate the temperature and the vapor composition. And then for the next point, we will change the liquid composition, keep the pressure the same. We will calculate new temperature and Y. Like that for every point, for given pressure fixed, composition changed, liquid, we calculate temperature and Y. So the calculation here then needs to start with a guess of temperature. And with the guess of temperature, we will calculate the vapor pressure. We will put the vapor pressure, we will put the X, we will put the pressure that is known. we will calculate the y. If the summation of y is not equal to 1, then we will give a new temperature and we will repeat. If it is very, very close to 1, like 10 to the power minus 6, then we stop and we start with a new composition. So we repeat the calculations from x equals 0 to x equal 1 with steps of 0.1, and that gives us, you can see the pressure is fixed, the x composition is changing. For every x composition, we get a different temperature and a different y composition. And then we plot them. Once we have the PT, XY data, we can plot it in many ways, y versus x, t on the y-axis, xy on the x-axis, and many more. So that's how the phase equilibrium calculations are made. I showed you for a simple calculation, but we can easily put the fugacity or activity and repeat in the same way. Okay? So now let's see the kinds of equations we have. That is the property models. What are the equations of state? Ideal gas law, cubic equations of state, PC-SAFT, SAFT, CPA, predictive EOS, that is a combination of equation of state with Gibbs energy. And I will highlight these two models. If you look in the simulators, you will find all this list of equations of state. I just put some of them. There are many more, okay? So there are many, many equations of state. Almost every month, somebody is developing a new equation of state. So the cubic equation of state, there are many cubic equations of state. I'm showing you a general expression on the left-hand side with respect to Z, and you see the parameters that are needed to get the SRK or the Peng-Robinson. And on the right, you see the expression for the SRK equation of state with respect to pressure. If you convert this with respect to pressure or volume or compressibility factor Z, you get a cubic term, and that's why it is called a cubic equation of state. And this equation has A and B parameters, and within the A parameter, you have the binary interaction parameter Kij. And because you need to fit the Kij with molecular data, therefore it is not predictive. For every new binary mixture, that Kij needs to be predicted. Okay, so also one thing to note is that remember that the fugacity criteria for equilibrium is fugacity coefficients, not the pressure or the compressibility factor. So we need to convert these expressions into fugacity coefficients. So here is how the fugacity coefficient is obtained. We need to integrate from pressure 1 to pressure X at a given temperature composition. If we take the equation of state and integrate, we will get the fugacity coefficient, and that is to be used in the phi-phi approach. But if we want to use the gamma-phi approach, we also need the fugacity coefficient and the activity coefficient. So we also need the derivation, that is the derivative of the Gibbs energy with respect to the mole numbers at constant T, P, and N. And that gives us the relationship of the Gibbs energy with respect to activity coefficient. So we need to do this before we can do the check for the phase equilibrium, because for phase equilibrium, we need fugacity coefficients and activity coefficients. So here is the result of all the equations that you need to calculate the fugacity coefficient of a binary mixture, any two compounds. The first equation is giving you the activity fugacity coefficient. Then equation 2, 3 gives you A and B. Then equation 4 gives you Z, and so on. Normally people write only one equation like this that you see on the right, SRK equation P equal RT, and people think that it is just one equation that gives you all the results. You actually need to solve these 15 equations, and for a binary mixture, there will be 29 equations, 46 variables, so the remaining variables need to be specified. And this model analysis tells you also which variables to specify. So another interesting thing is that these equations 1 to 15 can be ordered in such a way that it will be lower tridiagonal form. So if you start from the top and go to the bottom, the last equation will be fugacity coefficient, and there is the iteration. So it's a non-iterative calculation because the equations can be ordered in a low tridiagonal form. If it is a PC-SAFT, it's a more complicated form. The Z is not cubic now, but is more nonlinear. And we need the M sigma epsilon plus association plus binary interaction parameters. And it is also, when you take the equations, it is not lower tridiagonal form. So the calculation of fugacity coefficient will need iterations. And remember that Z is not enough. Z has to be converted to the fugacity equation form. So how many equations do we need to solve for PC-SAFT for binary mixture? You will find out if you look at our paper, 190 equations. So compared to the cubic equation of state, which needed for binary mixture 29 equations, this one needs 190. Do you want to still use it? Well, it turns out that for some systems, no matter what you do with the Kij parameter for a cubic equation of state, you cannot get the accuracy you want. But you can get the accuracy you want with the PC-SAFT. So you pay for the time, but you get the accuracy. Other models, like the Gibbs energy models, group contribution or molecular with electrolytes. So here is a list of group GE models. The UNIFAC models are group contribution, the others are molecular models. And the electrolytes can be electrolyte version of the molecular models or electrolyte version of the group contribution. And there are spatial models for spatial systems like amine, mixed salt, that is water, solvent, and salt, or sour water, caustic, many more. So for each of them, there is a special model that handles these kind of mixtures. So again, we come to the groups. Remember that the groups form the molecules, and we needed the contributions. And here are two examples of it. But now what we are saying is that when it comes to molecules, you need the interaction between 2-methyl-1-propanol and ethanol to calculate the activity coefficients. Whether you do it by NRTL or UNIQUAC, you will need those molecular interactions, as you see in the equations in the middle. But when we come to the group contribution, we don't need the molecular interactions, we need only the group interactions. So we need an interaction between CH3 and OH. And CH3 doesn't need to know whether it belongs to 2-methyl-1-propanol or whether it belongs to ethanol. It just needs to know what is the interaction between CH3 and OH, between CH2 and OH, and so on. So from that point of view, it is predictive because we don't need the molecular interaction data. We just need the group interaction parameters. And any number of binary mixtures can be made from those groups. So that's why this is predictive. When will you use the group contribution as opposed to the molecular? We can also see that here, that as I said, the molecular interactions The green and the yellow are molecules around each other. But with respect to the groups, it's not the molecules which are near to each other, it is the groups. So the number of parameters can be large or small depending on the mixture. If it is a binary mixture, we just need one pair of molecular interactions, but maybe we need 4 groups to represent the molecule. Then we will need 4 pairs of group interaction parameters. So maybe for a binary mixture, the molecular system is better. But if it is a multi-component mixture and we need still 4 groups, whereas in the molecular, we will need more groups and more difficult to get. So then the group contribution can become better. So there are advantages and disadvantages for both. And here is the model equations for the UNIFAC model. I'm highlighting in red, that is the activity coefficient we need. And we can also order it in lower tridiagonal form. So the last equation to solve would be equation 1, and it is nice lower tridiagonal. So no iterative necessary. So calculation is very fast. And let me skip this in the interest of time. It just shows that there are lots of blanks in the group interaction parameter, and they need to be filled out. And it can be filled out by making atomic contributions. That is, for any group for which the group contribution is missing, if we create the group with the atoms, then we can predict the atom contribution. And in that way, we can fill out all the gaps in the parameters. Then let's look at the mixed. That is now the equation of state and the GE model will be mixed together to calculate the activity fugacity coefficient. And there are lots of models like that. And then there are special models like NRTL-SAC or Polymer. I will also not go into the Polymer, but I will go into the NRTL-SAC very briefly, and the COSMO-RS also very briefly. So the combined equation of state GE model, we take an equation of state like the Van der Waals equation that you see in the top, and then we write the fugacity coefficient expression that you see in the shaded equation. And in this equation, there is the A parameter, and we need to calculate the A parameter. The B is easy. We use an ideal mixing rule to calculate B. To get A, rather than use the interaction parameter that we used in equation of state for SRK before, what we say is that the GE by RT for equation of state is equal to GE by RT for a Gibbs energy model at a certain pressure. And then on the left-hand side, we write the expression for GE by RT, EOS. On the right-hand side, we write the expression for GE by RT with the GE model, which is summation of Xi, ln, gamma. And then in this expression, we do some manipulation and we get the expression for A. So what it does is that it does not need now the Kij, because it gets the Kij from the activity coefficient model. So this is very powerful and it is valid for higher pressures. So this is a very good way to do high pressure, non-ideal vapor-liquid equilibrium. And then I will show you the UNIQUAC electrolyte model. Again, the equations, it's not just 8 equations, it's more, 17 equations. And what we want, sorry. So 17 equations that can be solved. And again, we can organize this as a lower tridiagonal form, so it will not need any iterations. The total number of equations is given, the total number of variables. And these are the 2 sets of variables that we want to calculate: activity coefficient of the solvent and activity coefficients of the ions. The degrees of freedom can be calculated, which variables to be specified. If we specify all these variables, a lot of variables need to be specified, a lot of parameters need to be obtained, but if we can obtain them, we can easily calculate the activity coefficients and then we can proceed. And then the NRTL stack, in the interest of time, I will skip this and I will go to the COSMO-RS, which is quite interesting. Let's say we would like to calculate the Henry's constant for a gas I in solvent S. What we find out from COSMO is that the chemical potential of gas I in solvent S is given by this expression, where the integral term is showing the sigma profile. That can be obtained from Gaussian or other molecular simulation tools. And once we have the sigma profile, where the expression is given, this expression then inserted into the activity coefficient expression gives us the activity coefficient. And note that the mu IP is the chemical potential of gas I in the pure state. That can always be calculated. The chemical potential of gas I in solvent is calculated from the sigma profile. And then we put the activity coefficient, we put the vapor pressure at a given temperature, we get the Henry's constant. So instead of doing experiments, we can directly calculate the Henry's constant. Normally, one would do measurements and then calculate the activity coefficient through measurements and calculate the Henry's constant. So we can bypass the experiment and do the calculation directly. How good is it? One needs to test. Sometimes it's quite good, sometimes it's not that good. But when it is good, you save a lot of time and energy because you don't need the experiments. It can be also extended to vapor liquid, solid liquid, liquid liquid. So it's a very powerful tool. And then we can slightly very fast go on that we want to do this saturation curve, solid liquid. We want to get the blue curve. The condition for equilibrium is shown in the red equation. How do we start? If we have the database and have the values for heat of formation, melting point, then we can directly go and do the calculation. Otherwise, we need to predict those heat of formation and melting point. Let us say that we have the data from our property model. So we have put these, then we go to the next step. We need the activity coefficient. Do we have a database? No. If it is yes, we go all the way and we have finished the calculation because we directly put the activity coefficient. It is unlikely we will do that. But we say that we don't have the activity coefficient. We need to calculate the activity coefficient. We go to UNIFAC, PC-SAFT, NRTL, UNISAC. All of these will give us the activity coefficient. If we do not have the parameters for the activity coefficient, we need to get the experimental data to fit the parameters. And then once we have done that, we get 1 point. And we repeat that point by changing the composition or temperature, and we get the total curve. So what you can see is that it's a lot of work even to do 1 point of the calculation if the experimental data is not there to get the model parameters. So other issues, as we said, that if we want to calculate any phase equilibrium, we need to specify variables fixed by the model, parameters regressed for the model, variables fixed by the problem, variables fixed by the system. Once we have all of these, we can get some of these parameters from the model library and from the database. And then once we have all of these, we can calculate the desired set of property. And this will give us the activity coefficient or the fugacity coefficient, which then we will need to put in a phase equilibrium calculation routine. Let me skip this too. And then let me conclude by saying that group contribution offers an option for predictive models. However, the simple GC model have an accuracy of around 5 to 10%. If we need more accuracy, we have to go for machine learning, but we have to pay in terms of computational time and resources. I'm not sure if machine learning, I get the feeling that machine learning models are for machines, not for humans. Model development requires collection of data and analysis to identify outliers, as well as to find ways to subdivide and the problem into well-defined subproblems. Because of the nature of the new GC models, application of these models in product design, that is the reverse of property prediction, requires special solution techniques, such as hybrid techniques. We will see that in the next 3 webinars. Chemicals and their properties need to be carefully regulated because of the many harmful effects they are likely to cause. New property models are necessary, but also need to be carefully evaluated. Some of the new developments are very interesting, like the PC-SAFT, the COSMO-RS, the NRTL SAC, and so, like those. And these are the references. So if there are any questions, I will take them.
Okay, for the first question, what is the complete reference of Gani et al. FPE in 2006?
I've included the reference in the list of references.
Okay. The second question, are the slides going to be available for us?
Yes, it will be. Here is the reference. Oops. The slides will be available. Here is the reference. And yes, the slides will be available. We are trying to set it up so that all participants can download the slides as well as the recorded sessions.
Okay.
Any other questions?
What are the disadvantages of mixed EOS and GE models?
The disadvantage is that I would say, maybe Professor O'Connell can correct me in there, is that whether it will work or not, there's no 100% guarantee. But the advantage is that we do not need, if we have fitted the GE model interaction group interaction parameters, we do not need the equation of state molecular interaction parameters. That's the advantage. Whether that extrapolation from the low pressure to high pressure will work or not, some cases it works, some cases it does not work. So one can do a fine tuning if necessary. But we are talking about using parameters that have been fitted at low pressure to applications that are at high pressure. It's purely predictive in that sense, but that's the good part of it. Any other question?
Please elaborate on COSMO-RS and its application. Thank you.
Again, just like I showed you, that for any molecule, the COSMO-RS method and also the COSMO-SAC, they are different in terms of how the sigma profiles are obtained and used. But once the sigma profile is obtained for a molecule, those sigma profiles can be used to calculate the activity coefficient of the compound in a solvent without requiring any experimental data. So that's the power of it. The disadvantage is that it works for some systems, but not for all systems. So it's very good if we know that for these systems it worked, then we do not need the experimental data. What people are doing, including us, is because sigma profile is not easy to obtain. One has to do molecular simulation with Gaussian or other tools to get the sigma profiles. So if we can generate enough sigma profiles and convert it into a group contribution method, then it can be very fast to do it. At this moment, it's not that easy to get the sigma profiles. But the developer of COSMO-RS method, Clamped, he has a software company and he sells his software which does the sigma profile and the activity coefficients for liquid-liquid, solid-liquid, vapor-liquid equilibrium. Okay. Any other question?
Are there any cost-free database where we can access experimental data to validate thermodynamic property models?
I didn't understand the first. Can you repeat the question?
Are there any cost-free database where we can access experimental data to validate thermodynamic property models?
I see. Cost-free. Up to now, our database is cost-free, but some time ago, the UNIFAC consortium had a database that was free. There are actually free databases, but they do not have all the compounds and all the data. They have a limited number of data, which is free. And then after that, one would need to pay for the data. But if you search in the literature, I think the best place to get cost-free data is the NIST database. Maybe in future they will also ask for a price, but up to now the NIST database is free. Any more questions?
Okay, one more question. Why TC and PC are the best predictive property by GC method, but not the VC?
Good question. I wish I knew. We can do this very well for TC-PC, but not for the volume. Maybe volume has some other. VC is well predicted with the machine learning, but maybe we need to take some interactions that we are not able to find in our simple expression. So that could be the reason. In principle, density is more difficult than the TC and PC. Okay, so we are already past 5 minutes. I don't want to take too much time of Professor John O'Connell. I will stop here and stop sharing.